Numerical integrations are used when symbolic solutions are impossible. For example, the result of the integral from 0 to pi square root of 1 plus cosine square of x dx has no closed form solution. One of the two methods that we're going to learn today is the trapezoidal rule. Let f be a continuous function on AB. The trapezoidal rule, using n subintervals in approximating the definite integral, is given by b minus a all over 2n times the sum f of x sub 0 plus 2 times f of x sub 1 all the way to 2 times f of x sub n minus 1 plus f of x sub n. Note that the coefficient for the two endpoints are 1 and the coefficients for the points in between are 2. Moreover, as n goes to infinity, the right hand side approaches the actual value of the definite integral. Recall, in order to find x sub 0, x sub 1, and so on, we use the formula delta of x equals b minus a over n, which gives you the width of the subinterval, and x sub I equals the first point a plus I times delta of x. Let's take a look at an example of how to use the trapezoidal rule to approximate a simple integral for n equals 4. First, we want to draw the function f of x equals x squared on the interval 0 to 1. Next, we need to find delta of x using the formula delta of x equals b minus a over n. b equals 1 in our case, a equals 0, n equals 4, so delta of x equals 1/4. Our first endpoint x sub 0 is 0. Endpoint x sub 1 we can see is 1/4. X sub 2, 1/2, and x sub 3, 3 over 4. X sub 4 is the right endpoint, 1. Now we have our value for x sub n. We can apply the formula. So to approximate the integral from 0 to 1 x squared dx will approximately equals b, which is 1, minus a, 0, divided by 2 times n, which is 4, multiply by f of 0. Since f is x squared, so it will be 0 squared plus 2 times x sub 1, so 1/4 squared, 2 times x sub 2, 1/2 squared, plus 2 times x sub 3, 3 over 4 squared, plus the endpoint, 1 squared. Now if you plug this expression into your calculator, you will get the value 11 over 32, which is approximately 0.3438. Just to see how well the trapezoidal rule can approximate the integral, we can calculate the exact value for the integral from 0 to 1 x squared dx. According to the fundamental theorem of calculus, we write the antiderivative of x squared, so it's x cubed over 3, evaluate from 0 to 1, and the answer is 1/3, which is approximately 0.3333. As you can see, the trapezoidal rule approximates the definite integral very well even when n equals 4. We'll take a look at the surface rule. Again, f is a continuous function, but at this time, n be an even integer. The Simpson's rule using n subintervals to approximate the definite integral is given by b minus a divided by 3 times n multiplied by this sum, f of x sub 0 plus 4 times f of x sub 1 plus 2 times f of x sub 2, and so on. Notice the pattern for the points in the middle are 4, 2, 4, 2, 4, 2. Because n is an even integer, we will always end at 4. So we add all the way to 4 times f of x sub n minus 1 plus f of x sub n. Again, as n goes to infinity, the right hand side approaches the actual value of the integral. Let's take a look at an example of how to use the Simpson's rule to approximate the same integral that we have done before with n equals 4. Earlier we have x sub 0 equals 0, x sub 1 equals 1/4, x sub 2 equals 1/2, x sub 3 equals 3/4, and x sub 4 equals 1. According to the Simpson's rule, we can approximate this integral by using the formula b minus a over 3n times the first endpoint f of x0 plus, again the pattern is 4 f of x1, 2 f of x2, 4 f of x3, and we end right here, and plus the last endpoint f of x4. Now plug in all the value into the formula. B equals 1, A equals 0, so we get 1 over 3 times n is 4, so it's 12. F of x0 is 0 squared, plus 4 times f of x1 is 1/4 squared, plus 2 times f of x2, 1/2 squared, plus 4 times f of x3, 3/4 squared, plus lastly 1 squared. Again, plug this into your calculator. You get exactly 1/3, which is approximately 0.3333. As you can see, using the Simpson's rule with n equals 4, we get the exact value of the definite integral.